Okay, hello everyone. My name is Vighnesh. I'm a PhD student at Berkeley, and I'm going to talk about the Hammer VLSI flow that allows us to go from the RTL that's generated from Chipyard down to GDS for a particular design and technology. So over here, this is just the overview of all of the stuff inside a Chipyard. We already talked about, going from the custom SoC config or RTL generators and ultimately generating the Fertile. And we went down this path towards getting behavioral Verilog and running software RTL simulation. And in this talk, I'm going to talk about going through the VLSI transforms parts and of course the backend here, which is the Hammer automated VLSI flow. So let's jump right into that. So in this talk, we'll first go over some of the applications of Hammer, some of the issues with traditional VLSI flows and how Hammer rectifies some of those issues, the abstractions that Hammer uses, a little example about how a PowerStraps API was developed in Hammer, and also the community development that's going on with Hammer. So let's get started with the applications. So Hammer has been used in Berkeley for real tapeouts for a very long time. So starting off with the Raven 1 chip back in 2011, this is one of the earlier RISC-V core tapeouts. This was done in Verilog, and very quickly soon after we moved to using Chisel for more of our tapeouts. And you can see some of our latest chips have gotten really big. They use Chisel 3 and also the BAG2 Berkeley analog generator to generate analog IP such as PLLs and SerDes. And notably here, the chips have increased in complexity, but the teams have still been relatively small. It's only groups of a few grad students who work on each of these chips. And it's really because of the knowledge that we've been able to encode in Hammer that we made this possible. A lot of the knowledge from previous grad students working in previous technologies that we have experience with is encoded in Hammer technology plugins. And as a result, we're able to leverage that for the future tapeouts. And these use a variety of technologies. So going all the way from like 45 nanometer down to modern 16 and 12 nanometer processes. And so now we'll talk a bit about, the chips that Hammer was able to produce. So here's a listing of chips going from Eagle, and now we have this like hyperdimensional computing core all the way on the right-hand side. We have ASPLOS, which is a Bluetooth chip. So you can see that these are like a wide variety of different chip architectures, all designed using Chipyard, using custom accelerators. And you can also notice that they're all taped out in different nodes. So some in like 16 nanometer process, some in 22. ASPLOS was notably taped out in Google's open source Skywater 130 process, which Hammer also supports. They were signed off at different frequencies. And notably, Hammer does support hierarchical design. So some of these chips you can see use different amounts of hierarchy and abutment. And notably on the last row, you can see that as time has gone on, the number of person months that you need to develop a new chip using Hammer as the RTL-to-GDS automation tool has gone down and down because of the knowledge we've been able to encode in Hammer's technology plugins. And of course, Hammer is not just used for like academic tapeouts that grad students do, it's also used in courses. So we use Hammer in our undergraduate digital design courses. So over here is like a link to our EX151 class. This is our intro digital design course. And our undergrads use Hammer to take designs from RTL, run them all the way through the tools using ASAP 7 and Sky 130 technology plugins using the Cadence toolchain. We also have a tape-out class that we started at Berkeley. So this was started quite a few years ago, but very recently in spring 2022, we had a bunch of these chips over here taped out in the middle. Berkeley ML, which is a ML multi-core system, has a bunch of RISC-V cores, has some ML accelerators, and then we also have the SCUM RISC-V chip here, which is RISC-V core plus like a few Bluetooth components. And we also have chips like the Sky 130 MPW chip, which contains like RISC-V core and some analog IP. And I think Jerry passed around the chips that you saw over there. These were taped out just last semester. And so they came out of this tape out class. They used Hammer to design all of those. Okay, now what does Hammer support? So Hammer has, for the proprietary section here, we have like technology, and we also have the tools. So technology, we support many different technologies from different foundries. You can probably guess what they are based on the nodes that we have here on the right. We also support educational PDKs, ASAP 7 and Free PDK 45, as well as the Skywater 130. And on the right here, we have all the different tool plugins. So we typically support most of the Cadence and Synopsys tools, although our plugins are most mature for the Cadence toolchain for synthesis and PNR. And we usually use caliber and ICV for DRC. We also support power simulation using cadence joules and voltus. This also includes rail analysis, EMIR analysis, and conformal and Yosis for LEC. So I want to highlight how Hammer is able to help us reduce the amount of design-specific lines of code we need as we continue using a particular technology and tool. So you can see here, these are just chips on the x-axis, and we have plotted the number of design-specific lines of code, the lines of code in a given technology plugin that chip used, the aggregate number of lines of code, and the percentage of unique lines of code. And so what you can see here is that, as time has gone on, the number of unique lines of code we needed for every chip keeps going down because we're able to encode the knowledge for using a technology, for a given process, for a given tool, into the plugins for that tool that allows the knowledge reuse. And what you can see here is that for a chip that was designed in the same process, as you go from chip to chip, you can see that the number of lines that we include in the technology plugin goes up because we learned something about the technology, we added that shared knowledge to the plugin, and then the number of unique lines of code that we need to run that chip goes down. So reusability is very high. And I want to point out here on this previous slide, you can see that on the latest chips, we have like single-digit % of unique lines of code. And this means that most of our flow is kind of automated at this point. There's very little tweaking that you need to do. Coming out of Hammer, you get a pretty reasonable RTL-to-GDS flow that works 90% of the time. Of course, it never works all the time. So one size doesn't fit all, right? And that's kind of one of the issues in traditional VLSI CAD flows. So if you guys are familiar with the typical ASIC flow, you start off with RTL and you go through these tools, right? So we have synthesis, place and route, and then we have a physical design that we take through DRC, design rule checking for a given technology, and the LVS. We want to check that the net list that we have coming out of the place and route tool matches the actual geometry in the GDS. So we extract the transistors from the GDS and we compare them against those in the net list coming out of PNR. So this is a traditional ASIC flow, and Hammer doesn't change this. Hammer still has the same steps here: synthesis, place and route, DRC, LVS. We just package them nicely. So what are the components of like these VLSI flows, right? So we start off from the design aspect. So here we have the RTL, we have the hard IP cores you have in your design, you have floor plan that is specific to your design, and all kinds of timing constraints and power constraints that are also specific to the design. Then you have the technology. So this can be Intel 16, TSMC 5, Sky 130, many of these. And finally, you have the tools. So how do, for a given technology, for a given design, how do you invoke the tools? And this can be simulation with VCS or synthesis with Genus or running a PNR flow with the Open Road. So why is physical design so hard traditionally? Well, it's because these VLSI flows are built custom for every project. So we have these tool design and technology concerns, and the flows are designed kind of to intermingle all of these concerns. So if you have a different design, then you just mutate the constraints. If you switch the technology, you have like new rules, IPs, different SRAM compilers. If you have a new tool, then perhaps the commands have changed, common UI and cadence tools, for example. And so we take all this like design intent and expertise and we tie them up into these big monolithic scripts, right? The tool design and technology concerns, they produce some big tickle script. And that can be a problem when you want to migrate technologies or you have a slightly different design. And we have a wide range of technology options and domain specialization. So we want to do like large scale architectural exploration across technologies, across different tools. And we can't do this with these non-reusable monolithic tickle scripts. So concrete example of this is power straps. So at the very top level of our chip, we have bumps. Those deliver VDD and ground, and then we ultimately need to get them to the transistor. And so typically what's done is you take your metal layers, each of them are routed in a different direction, vertical or horizontal. So you take the certain metal layers, you create power straps on them, you route them to the top level VDD ground bumps, and then you keep doing that as you go further down in the chip, and your power grid gets more fine and fine as you go further down to the transistors. And then you generate vias down all the way. So this is hypothetically how you might create power straps using some commercial CAD tool. So you set some option for M1 and M3, and then you use this like create power stripes command. You have to specify the nets, the power domains. You specify which layer you're creating the power strap on, the routing direction, which layers the vias go between, the pitch, spacing, width. These are all like technology level concerns, right? And then you have design level concerns like the bounding box of a given module that you want to put the power straps on. And then finally, you want to specify like where exactly the straps ought to start and end so that you do not have like weird offsets or off-grid power straps. So you can see here that we can separate this huge command into 3 pieces. So we have the tool-specific piece, that is the command and the options. You have kind of the DRC, ERC compliant dimensions. So these are kind of specified by the technology, which metals we want to use, the routing direction, the minimum spacing, maximum spacing, things of this nature. And then we have the design specific things, the module we actually care about, the actual power domains in our design, the group pitch, which governs the power grid density and things of that nature. So this is the issue with like traditional flows is these concerns are kind of put into one big script. If you change something about your design, you change something about your technology, or you use a different tool, now everything here has to change. So it becomes difficult to kind of explore a larger design space. And so how does Hammer fix this? So I'm going to go over some of Hammer's abstractions in the next section. So Hammer is really about the separation of concerns. So we take these like a design, tool, and technology specific concerns, and we try to separate them into individual plugins for each design, tool, and technology. We also do standardization. So Hammer defines an intermediate representation, a consistent schema for constraints, options, and files. And these are in JSON or YAML formats. Hammer is also modular. So you can take tool and technology plugins, you can share them with other people, and you can integrate them. So if you have an open road tool plugin and you have a Sky 130 technology plugin, you can snap those together and get a Tickle flow that works with both of them. And of course, we support incremental adoption. So you can always inline pieces of Tickle from your traditional flow into the things that Hammer generates so that you can use your custom solution along with what Hammer generates. So I talked a lot about Hammer, but we finally want to get to what is Hammer? At the end of the day, what does it look like? So Hammer is a Python framework for abstracting and building these standardized VLSI CAD flows. Hammer is not a CAD tool, to be clear. It's not re-implementing synthesis or PNR or any of these things. Hammer is invoking those tools, and it's doing it in a very consistent, managed way. So it generates these Tickle scripts, and it manages the execution of the underlying CAD tools. And Hammer has been proven, of course, for architectural exploration, for teaching and designing all of our research chips. And of course, Hammer is open source. Hammer started back in 2015. We've been using it in our chips since 2016, in our classes since 2019, and the repo is currently about 35K lines of code. So a lot of development has gone into Hammer. So here's like overview of the software architecture of Hammer. It may seem a little busy, but we'll walk through each of these sections in the subsequent slides. So first at the very top here, you have kind of your Hammer intermediate representation. This is like a standardized data interchange format where you can specify constraints, options, and intermediate files and so forth for a given design or for the way you want to use a given technology plugin and so forth. So humans can just write YAML to describe their design. So over here, I have a design. I might want to specify how the UPF ought to be generated, what clocks are in the design, and so forth. And this allows us to kind of de-embed the designer intent and expertise from the Tickle script. So the designer no longer deals directly at the Tickle level. Instead, that is the job of the CAD engineer. In our case, we're the same people, but perhaps you may want to decouple these. The engineer is able to instead just directly write to this YAML description, which is a very nice, clean way to separate the intent from the actual implementation in Tickle. And Hammer also supports a form of Iyer metaprogramming. So you can take any of the keys defined in this YAML file, and then you can selectively modify them using these metaprogramming keys in the Hammer IR2. And the nice thing is you can track the history of how those modifications happen, and there's also type and validity checking. So all of the things in this Hammer IR specification, they are well typed. You know the type of them, and Hammer will also check the type is consistent at runtime. And this gives us a mechanism for partitioning and customizing the design intent. So you can have things that deal with, you can have YAML files that deal with particular hierarchy partitions in your design, and then you can have one that deals with a chip top, for example. Okay, so we have these tool and technology plugins I've been talking about. So what do they actually boil down to? So on the left side here, you have the technology plugins. They consist of a JSON file, which points to where a technology lives in a given file system and all of the underlying collateral of that technology, all of the lib files, its left files, its techlef, and things of that nature. Then you have like the default Hammer IR. This defines a lot of the default keys for that given technology. So for instance, if you want to select a simulation option that must be present for this technology, you can specify it in this file. And then you can have this like init.py file. This is like top level Python API for your technology plugin. And this is where you can make modifications to the PDK. For instance, you may need to hack the PDK to like scale some GDS files or add some labels in your lefts. This is also where you specify how the memory compilation works. So you can either call out to an SRAM generator or you can use the cached SRAMs. And all the technology-specific flow actions are also encoded over here. Finally, in the middle, you have like a hammer. So the hammer is what like parses the configs of the technology plugin, and it also invokes the init.py file to construct the technology library as an in-memory object. And then to actually interface with it, you have the tool plugin on the right. So tool plugins work similar to technology ones. They have kind of a default settings that you specify in your defaults.yaml. And then your init.py is what actually constructs a tickle file for a given setting. So given the settings from the technology plugin and the settings from a tool plugin, the init.py will construct a tickle script such that it generates what your intent was. So this is where you specify all the default commands, how you implement the different Hammer APIs, execute the tool, and parse the errors and look at the metrics. And one thing I want to mention here is that these plugins can be swapped out with other ones because all the data interchange happens in the Hammer IR. So for instance, you have two different tool plugins that implement the same synthesis API. In theory, you should be able to swap them out. Although in practice, there can be some specific situations, some specific things you want to do with one tool, but not the other. Hammer also gives you a nice way to encode those special cases. So Hammer supports this thing called hooks, and hooks allow you to tap into the steps that are within a given tool plugin and inject a tickle in the middle of them. So we can replace, modify, insert any of the steps in a given flow inside a tool by injecting tickle with these hooks. And typically this is written by the designer or it's applied by a technology plugin. So a designer can use it to like override some specific setting for generating some fragment of tickle. A technology plugin may be able to override it for doing some technology-specific instantiation or things like that. And finally, the way the user interacts with Hammer at the very top level is using the Hammer driver. So you specify this design VLSI. This is something that extends from CLI driver. And then you can invoke design VLSI from the command line. You give it your configs passed as YAML files on the command line and then some given action. And so this is the top level CLI interface for Hammer. The CLI interface itself is usually wrapped with makefiles, and Hammer can actually generate those makefiles for you as well if you want to do kind of a vanilla synthesis all the way to PNR, LVS, DRC flow. So let's go through a quick example of the PowerStraps API implementation in Hammer. So remember that before we had this complicated fragment that was very specific to a combination of a design tool and a PDK. And now we want to find a way to extract that into a higher level API. So to specify the PowerStraps, we need to know the DRC rules of that process, the target power dissipation of that given module, some Iyer drop spec, and also the power domains for that module. And we can also do hierarchical in Hammer. So that might add additional physical constraints. So if you have tiled modules, you need to make sure that their pitches match. And it's very easy to make mistakes when you rework the hierarchy or you slightly change the dimensions of a given block to make sure that the tickle is updated correctly. So the goal of Hammer is to make that process automated and code that as part of the tool plugin. So we don't want the designer to do math. We want to codify this design process in technology and tool agnostic code. And the way we do that is we look at the valid pitches for any hierarchical design. We calculate offsets for all the hierarchical blocks for where the power strap layouts ought to begin. We generate these layout optimal DRC clean straps. And in order to do this for the user, we specify intent at a much higher level than just these length units. So usually designers shouldn't want to work at that level because length units are typically going to be particular to a given PDK. We want to specify this like by track specification of how we want to lay out our power straps. So here's an example of how the by track specification works. So we say I want to generate power straps, and here I have a bunch of routing tracks for a vertical metal layer, and I want to generate these power straps by tracks. So how does this work? I specify the width of a given track of a given power strap. So here I have 2 power straps for VDD and VSS. Each of them are 4 tracks wide. And I have 2 power domains. I have 4 tracks. I have 2 domains. So that means there's going to be 8 tracks per group of power straps. Fine, then I can define the power utilization. So 0.5 here means that if I take my tracks per group, divide it by the utilization, then I get my group pitch. So that's the number of tracks in the middle of each group that are going to be used for routing. Then I specify all the layers on which I want to construct power straps. So notice here, I don't specify the routing directions for each of the layers, right? Because that is specified by the PDK plugin. And now this is like the description of how the straps ought to be generated that Hammer understands from this. And then we let, after the power straps go, we let the router do its thing, do its detailed routing. It fills in all the tracks in the middle with any of the routes it needs. And so here's an example of how this works. You can just change one number and you immediately get a new DRC clean valid power straps implementation. So you change that power utilization from 0.1 to 0.3, and here's like an innovis view of like your circuit. So you can see utilization 0.1, these are very sparse straps. 0.3, the straps become a lot more dense. And so there are different cases in which you might want either one of them depending on your Iyer drop spec and how much power you expect to be dissipated. Okay, so given that example, I want to just dive into some of the community that's been building around Hammer. So we want to emphasize that everyone can use Hammer. And Hammer gives you like a lot of sensible defaults and also gives you hooks in order to override them for a particular design or PDK. So we have a bunch of sensible defaults for like a very typical RTL-to-GDS flow. So all of the actions are already defined for you: synthesis, place and route, LVS DRC, post-synthesis, and post-PNR simulation as well. We allow automatic generation of timing, SDC, and power CPF constraints. We generate these power meshes, as I just described, from high-level parameters. And there's also a makefile that Hammer generates that automatically implements this flow graph by calling to the Hammer CLI under the hood. And on the right, you have these techniques to override each of these defaults depending on the very specific design things that you have in mind. So you can use hooks to inject your own steps inside any tool plugin. You can use your custom SDC and CPF files. You can use like your Foundry provided or your very own power mesh generator in lieu of the Power Straps API that's built into Hammer. And instead of using Hammer's generated makefile, you can run Hammer on the command line, or you can write your own custom makefile if you have a flow that's perhaps reentrant. And the result is that you get 80 to 90% of the way there of getting a clean, DRC clean RTL-to-GDS flow out of the box. And this allows you to very easily learn the VLSI flow and get early design feedback. And in Chipyard, we have examples for using Hammer to do RTL-to-GDS for ASAP 7 and Sky 130. And everyone can use Hammer. You can also contribute to Hammer. So because of the way Hammer is designed, you have this like very modular override hierarchy where the technology plugin can override the settings in the tool plugin. The design-specific things can override things in the 2 other plugins that we have there. So you can have the 2 designs, A and B. They have their own hooks and their own API. You may want to take any of the common hooks that both of these designs use and merge them into a technology plugin. Any common APIs can also be merged into a tool plugin. And you might have many different tech plugins. And if there is some common feature you find in there that could be added to the Hammer IR, that's something that can be ported upstream to Hammer as well. And of course, the same also applies for tools. So some recent changes to Hammer. So as of a month ago or so, Hammer has been now published to PyPy, so you can like pip install it and play around with it quite easily. It's also installed during this typical Chipyard build setup, so you can play with it inside of Chipyard. Hammer is now a poetry project. It has built-in CI now. It has unit testing, and we have type checking too. So Hammer is a well-typed Python API. You can use MyPy on it and everything works fine. And the other great thing is, thanks to the generosity of Cadence and Synopsys, we now have public Cadence and Synopsys plugins as part of the main Hammer repository. So everyone can use Cadence and Synopsys Flow. No need to bug us for plugins. However, the mentor tools are still proprietary. So if you do need access to those, there's a link at the end of this slide deck. And just as an overview of how this works, here's like RTL-to-GDS flow using Chipyard to define your design and all of the open source tools to go from RTL to GDS using Sky 130 PDK. This is using like the Yosis for synthesis, Open Road tool chain for place and route, Magic for DRC, and NetGen for LVS. This is a fully open source flow. If you want to do this for a chip top, it takes about 6 hours, and Rocket Tile takes about 30 minutes. And we have a very similar tutorial to this with commercial tools that use the Cadence flow, Genus and Innovis. So in summary, physical design is very hard, and there's a good reason why we love staying in the realm of models and writing RTL. The chips are growing in complexity, and we have this like huge evolution of the EDA and PDK stack. And Hammer is a very useful tool for separating these design tool and technology concerns. It enables the reuse of a lot of code that you used in older designs in new designs by encoding your design knowledge into a standardized Python library that everyone else can use. And you can do very easy power and area evaluation. Now using Hammer, you also have open source EDA tools thanks to Open Road. And we also have open source PDKs thanks to Google. And Hammer also, of course, works on commercial EDA tools. So a few things about the future of Hammer, things that we're planning right now. More tool integration. We want to be able to parse metrics right from the tool log outputs, some feedback on constraints to know when they're valid or not. Someone earlier mentioned that we generate this huge chip knock config. How do you actually floor plan that? So we're working on an aspect-oriented chisel floor planning API so that you can get that collateral out of chisel and then use it in your floor plan design in Hammer. We're working on an abutment and partition-based hierarchical flow instead of doing top-level PNR. Working on a true multi-clock and power domain for DVFS supports. And of course, there's a lot of dev work that keeps happening, and it usually goes along with our tape-out cycle. So there's a bunch of ideas. If everyone's interested in helping out in Hammer, please come by and talk to us. And if you want to learn more, here's our GitHub link. There's also a very small end-to-end example of doing RTL to GDS with the Cadence tools inside the Hammer repo itself. If you want to just do a very quick, small example independent of Chipyard. There's also documentation, including the integration with Chipyard. You can go to our discussion forum on GitHub, ask us any questions. If you need access to any plugins for a tool or technology that's proprietary, please email us at this address. And of course, we have our digital design labs from 151. They are all going to be published here, and you'll be able to run them using open source PDK and Cadence and open source tool chains. So with that, I hope you guys enjoyed the presentation and looking forward to your questions. Thank you. Yes.
Can you comment on the example ASAP situation?
Yeah, so I think Skywater has been tested thoroughly with Open Road, ASAP 7 a lot less so. If you have any specific things that you're dealing with as you're working through them, please reach out to us. I think we have at least some small designs working, but being able to get like very large designs to go through completely DRC and LVS clean is not that easy. Yes.
You usually would say you don't go easily and cleanly. Do you then try to fix Gamma plugin parts, or do you then manually engineer?
Yeah, that's a great question. So like the first time you see something wrong in DRC or LVS, you usually start by introducing hooks in your design script. And then you figure out like, what are the modifications we have to make to the tool or the PDK in order to make things work. Once we accumulate enough of those hook changes inside a specific design, then we decide to like push those up to the tool or technology plugin. So yeah, we try to first off like pipe clean things for a given design, and then once we find common things that need to be fixed across many designs, we push them all to the tool or technology plugin, and that's how we keep the knowledge base growing from tape out to tape out. Okay, thanks everyone.